and today is 13th. And we're gonna finish the course on the note QCD, going down to grand unification. From QCD, we started the things that we learned yesterday about QCD. But I just want to be sure that you don't want to ask me questions about what we said at QCD. Remember what we said? Let's just summarize the QCD while you are thinking whether you want to rise. It's a gauge theory of strong interactions. Based on SU3 color, quantum chromodynamics, never wrote it, but you heard of it before. Chromodynamics, chromos. Is because there are three colors. We said the quantum numbers associated with the quarks is color, so we gauge it. Color is gauged. So that means 8 new messengers, the gauge bosons that we call gluons. And well, let me ask you a few questions. We'll 8 gluons. So the quarks come when I say that there is a quark. Really, the quarks really is coming in 3 colors. Like, let's choose this is not seen. Is this seen? No. Yellow is not good, right? Maybe this one would be better. I'm not sure. Well, let's put blue and say green. Right, this is this SU3 quantum numbers. These are the 3 colors. And we said the weak interactions, for example, so we have up and down quark, right? Up and down quark. And so the weak interactions are vertical. They take up to down quark, let's say left-handed. This is what W does, vertical. Weak interaction. Whereas it goes like this, a quark green quark can become a blue quark or red quark, it's the same quark. So we have a horizontal interaction, which is strong. Strong interaction. This is the difference between. So you see, they are orthogonal. This is what we say. The way they're all orthogonal to Lorentz transformations and so on, we have the gauge transformations are orthogonal to each other. Okay, so the gluons, this is what is done. This is what the W does, and this is done through the gluons. So gluons have sort of double color, right? A gluon takes a, so a gluon that takes a green to blue is really, we could call it, anti-green blue. It has a double color. Right, that's what it does. That's how would you depict it. Okay, let's do it again. Let's do it in color. Let's take the green one. And then it becomes blue. So what it emits here, I don't know how to draw it even, right? It's this gluon. How do I do anti-green? I don't know how to do that. It's sort of right. The guy does that. Okay, this is our gluon. That's what we said. And that all happened is from the covariant. We knew how to write the Lagrangian. The famous, beautiful, simple Lagrangian is just the analog of Maxwell. Each quark couples to gluons and quarks have masses. Of course, this mass comes, as you know, this is not some God-given input. This mass comes from where? Where does the mass come from?
Higgs mechanism.
Right. There is enormous, rich, beautiful physics, which I just put the mass term. All I'm interested in now is a strong interaction. Higgs carries no color. Remember, Higgs is colorblind. Who else is colorblind? Photon is colorblind. Who else is colorblind?
Leptons.
Huh?
Leptons.
Yeah, sure. Leptons don't even know about it. But these guys do couple to quarks. It's different. Leptons don't know anything. These guys do couple to quarks. Okay, you are right. Leptons are colorblind. But I meant the messengers of the forces that actually couple to quarks. All of these guys couple to quarks, but they're all colorblind. They cannot distinguish from one color to another. For them, they are equally. That's why I can study QCD separately from other interactions. I can study electromagnetism. I am Feynman. I don't have to think about strong force. It's going to be completely orthogonal. Whatever I conclude about QED is okay. That's what we said. The thing, of course, the crucial thing, it's all here. This is the crucial thing. Whenever you write a gauge symmetry everywhere, there is a strongly coupled theory at low energy, so I call it G strong, often called G3 or G color. And then there are the generators. I took alpha to be the 1 to 8. And these generators satisfy some commutation relations. We don't even have to know them, because we know how to build them. Oops, what happened? And you remember what we said? T alpha, how do I contract them? I put Pauli matrices sigma 1 and sigma 2, of course, divided by 2 everywhere. I can, that's 6 places. And then there was Cartan. T3, T8 is Cartan. Diagonal. They are all normalized. This is the summary of what we said. That will be always true. Is 1/2 delta alphabet. So for example, T3, I won't write it, must be proportional to 1 minus 1, 0, must be, that was a choice, the first one, and then T8, and you figure out the constant of proportionality. It's very easy to construct SUN theories. It's all about Pauli matrices and Cartan is very easy. And then we said that when you have these hadrons like proton, there is also, its proton is full of glue. Actually, I shouldn't draw it like this. Let me, if I draw my proton, there are here some 3 quarks, tiny light quarks, but it's full of stuff here. It's full of propaganda. This is full of glue. There is glue inside, the gluons. There are also the QQ bar pairs. They are floating around. It's a very dynamical, dramatic environment. The mass of the proton is the kinetic energy of gluons and quarks. It's not just made out of quarks. Gluons are fundamental there. It all comes from kinetic energy. M up is very similar to M down, and it's just few MeV. This is much smaller than M proton. It's 0 at this scale. This is remarkable that all of our mass, somehow there it is, you know, God's particle, they call it the Higgs, and apparently gives the mass to all the fundamental particles in this world, but not to us, not to you and me. We have absolutely no knowledge of the Higgs. It's so secondary that all of our mass comes from this strange dynamics that happens inside the gluon. So what we say is that will be roughly the summary. The quarks are confined in hadrons, in baryons such as proton and neutron, and of course mesons such as the pion. This is the world in which we live. Which means that alpha strong is some number which is much bigger one when the exchange momentum or energy becomes smaller than the mass of the baryon. Hadrons. Let's take proton, which is GeV. When you go to low energies, the coupling constant can be we have strong interactions. Strong interactions I put in quote unquote, because they are strong only at low energies. True only at low energies. And this is consistent with this beautiful picture that we said, that the coupling constant at some energy is the coupling constant at some other energy plus a logarithmic change. Most contribution comes from gauge bosons, if you have gauge boson in your theory. Some come from fermions, and even less from scalars. I mean, there is so little coming from scalars that you can basically forget about it. After all, the only scalar we have is just one Higgs doublet, whereas we have a lot of fermions, 3 generations of quarks and leptons. So this is a very tiny effect in the standard model. In the world in which we live, in the standard model. So we can compute this B. This is very nice. We know what the particles in the world are, so we will compute this B. By the way, there is a situation when the scalars could become important. It's called, a lot of you guys want to do ADS-CFT and superstrength and stuff like that. So I presume that you heard of supersymmetry. Is there anybody who didn't hear about supersymmetry? Supersymmetry, often called Susie. So all of you heard about, what is supersymmetry? Who can tell me? This is a digression. Nobody says. Everybody heard of it. So what is it if you heard of it? Are you there?
Yes, we're.
Okay. You want to tell me, Severek, or someone else? What did you hear? What is it? It's supposed to be supersymmetry. What's so super about it?
You said there are many parameters the other day when you mentioned it.
Forget the number of parameters. What is it? If I ask you, what is a human being? You don't tell me there are 8 billion on the planet. No, you first define that, then we'll count them.
I mean, as far as I know, previously we had the Poincare symmetry, and then we
have a lot of symmetries. We have SU2, SU3, whatever. We have left-right symmetry. What is?
Yeah, but we expanded the Poincare symmetry to some other symmetry where we, for example, in Poincare symmetry, if we consider the algebra, we think about the
too mathematical. It's too mathematical. It's okay. You can tell me like that. You see, I want you to go a little bit more in a nutshell. It's good. It's good. You're right. I can do that, but I want a little more. Now, the particles that, okay, let me help you. So the particles that you and I introduce and live with, we decided to separate into fermions and bosons. Fermions have spins. Bosons don't have spin. All the symmetries that you and I know in this world, I mean, it's sort of amazing. They are completely different fermions and bosons, okay? So normally the symmetries are the transformations of one fermion into another fermion. Poincare or not, these are names. Now, of course, suppose, I always like to do this. I have a nice test. I've been doing the following most of my life. In order to decide whether I'm working on something fundamental, I would go, and it was nice if I could talk to a girl in a party or a cashier in, in ICTP cafeteria. And if she asked me, what are you working on? It's sort of not easy to tell him, there is some Poincare symmetry. So, it's just, she won't be impressed, or he, or whoever. So I've often worked on the symmetry between left and right, that people say, oh, really? Oh, yeah, of course, that's fundamental. There is a symmetry. Why? What do you mean? Well, electron also comes left and right. So when you can do that, now, of course, fermions and bosons, that's not so easy. For example, I've been interested a lot, most of my life, in the question of magnetic monopoles. I'm sure all of you had a similar problem like me when I was a child. I tried to break a magnet. I was going crazy. How can there be always these two poles? I had an older brother. He would tell me, no, forget it. Sorry. And some 20 years later, I was like 4 years old. My brother comes home very excited. He says, you were right to try to break it. He just read Dirac paper. Dirac actually wrote the paper what the world would look like if there were magnetic monopoles. Now, that's very easy to explain to a cashier in ICTP cafeteria. Think of this, please. When you think they're doing important physics, think whether you can explain to a layman. The less words you need, the more likely you are actually doing something that may be fundamental. You know, imagine this guy Newton, people asking, what are you working on? I'm working on how the stones are falling down and how sometimes they're not falling down. So what do you mean? Look, Earth is not falling on the sun. That's even, you know, that's sort of, well, it's not easy to be Newton, I know, but still. So let me today is the last lecture, so I'm going to make it a little lighter. I'm going to summarize the basic physics and we'll just chat with you a little bit. Now, fermion and bosons, that's not easy, right? Here we have a problem. So I'm also failing. How do I tell the cashier that there is a fermion and a boson? Okay, I'm sorry. So maybe I should have criticized you. Maybe I have the same problem. But at least between you guys and I, we would say the symmetries normally when I have fermions. What we are used, what the symmetries do. Symmetry is some kind of operation that takes one fermion into another fermion. This is what we always done, one boson. All of the symmetries that we have, all. I don't know if any of you read Asterix, you know, so Asterix always says all. Well, there was a no-go theorem for many, many years by Coleman and Mandula. I don't remember the year, sometimes in the 60s, had a no-go theorem. Usually no-go theorems are wrong, which said that all symmetries must be like this. So you can imagine the excitement that in the early 70s, some people arrived at, they were called Gelfand and Lichtmann in 1971. Great mathematical physicist Gelfand. This work will be completely unnoticed. And then there will be Wess and Zumino, who will become famous as the fathers of supersymmetry in 74. There were other people contributing here. Actually showed that there is a way of going from a boson to a fermion. And that was very remarkable. You know, we all get excited. I'll never forget, 1974, I was a beginning graduate student, just studying my research. I went to a seminar at Columbia, Zumino. I'll mention two seminars which have shaped my life, very important. I've been fascinated by supersymmetry and worked a lot on it. It's a great speculation, so I'm ambivalent about it, but I also love it. So Zumino presented this beautiful thing that you can actually have a symmetry between fermion and the boson. And he said, I'm sorry, I have to tell you something. I think it's like a giraffe. You must admit the giraffe is beautiful. But what does giraffe serve? Well, it turns out he was wrong. Giraffes are very useful to get the leaves, which are very high. They apparently play a role in nature, very important. And supersymmetry from 1974, when Zumino says, forgive me for doing this, this is purely a game, he says, there will be no real physics here. This is 74. From 79, later on, it will become a dogma that the whole world will start to work on supersymmetry. Okay, this is very funny, how things can change, okay? From heresy, but that's typical, right? Think of our religions, right? From heresies, they become dogmas. From 1979 onwards, by the work, here's some guys called Witten, you may have heard the name, some other guys, will actually argue that Susie or supersymmetry plays a fundamental role in nature. It has been desperately searched for. We have to put question marks. It has not been seen, which doesn't mean it's not there. And the beautiful thing is that you actually, and the way you do it, it's like the following, okay? You can relax today. I'm going to mention two concepts. We can go make another coffee and so on. We got to finish this sort of lightly today. You can introduce something by the word, the revolution of how to work with supersymmetry. This was a field reserved to mathematical physicists until 75, I think. In 1975 or 6. I was trying to learn it, and I spent months and months of my life struggling with the algebra. When Salam and Strasdy, so it is the beautiful work done at the ICTP. Strasdy was my colleague for a while. He retired quite a few years ago. Developed a superfield. They made a technical revolution. Everybody could work on supersymmetry. And the way you could work, it's like this. You can write a superfield that looks like a scalar. Look, this is a scalar. So this is a boson. This is some scalar. Then you write theta plus F. This is a fermion. All the things that you need to know that theta is a funny number. It's called a Grassmann number. You have introduced a funny mathematical entity. Once you accept it, it's that theta I, theta j, anti-commute. These are funny numbers. Numbers normally commute. Anyway, what the proponents of supersymmetry say, that for every boson, there's a fermion. For every fermion, there's a boson. Gleschel said once, this is a beautiful theory, he says, and it's very successful. We already found half of the predicted particles. Okay. So what supersymmetry says, that if the world is true, if there is an electron, there must be a selectron. If you tell me that there is a quark, all right, there must be a squark. This is a fermion here? Well, obviously. So if electron is a fermion, this guy is a scalar. Squark is a scalar. So if there is a W boson, there must be, it's called a Vino. This is a boson. Sorry, this is a fermion. Agree? Why? Because W is a boson. What else? If there is a Higgs, there must be a Higgsino. You don't say Higgs, I guess it's. And of course, it's a fermion, and so on and so forth. This is what we have been looked for, and this is what you mentioned, that I said that there are many parameters. Unfortunately, when you want to work out homology, it's not a good theory. People even constructed something which is called supersymmetric standard model. So this is the standard model. The standard model, this is supersymmetric standard model. And very often we even say minimal. You can add minimal to it to make it minimal. Which means, this is just, why am I mentioning this? Imagine that tomorrow LHC finds all these guys. Tomorrow they find the selectron, then 3 days later they find the subquark, and then a week later they find the Vino, and so on. When we do the running, we must include those particles. You agree? When I write my contribution, I must include them. So when you want to follow your couplings, you have to know in which world you live. Keep that in mind. I don't want to say more about supersymmetry, okay? I could go on forever. Okay. The problem here is, okay, the problem is why you shouldn't work on the theory seriously, that you get about 100 parameters. A lot of new, it's not there is no supersymmetric standard model. This is a cheat. This is here really, the physicists can cheat just like everybody else because it's a collection of models. So for example, many of the practitioners in the field, they assume, for example, so what you do, you assume for simplicity that all the masses of the particles are the same. If P is a particle, this is a particle, a supersymmetric part. This is what Susie does for supersymmetry. Now that's kind of crazy, you agree? Think of our particles, then masses are so widely distributed that it's kind of crazy. If you don't do that, you cannot make a single state. Okay. Any questions here? In our chat, this is a chat today. Okay. Now, I finished yesterday on the interesting note that if it is true that the couplings run, and we could see that up to the energies of today, assuming that they keep running, that nothing dramatically changes by the rules of field theory, and I plot the coupling and I plot the energy, we actually, you and I can compute when the 3 and 2 coupling meet. This is the standard model picture. They meet at some energy. This is MGAT. And turns out that MGAT is predicted to be about 10 to the 16 GeV. So what, you will say? What's a big deal? 2 couplings meet. Then someone helped me, I don't know who it was, that if I want to build a minimal grand unified theory, where I put together quarks and leptons, we said this is, I don't know who it was yesterday who told me, it was SU5, right? So here would be a 5-dimensional representation. This is just an illustration, not a real lecture. So we said the first ring would be SU3, and here would be SU2. So let me imagine that I want to build my SU5 theory. Let's do it together. Give me a hand. So who will be here? Who is here? I'm you know, thinking of my fermions matter. Who is here?
Quarks.
The SU2 part.
SU3.
The leptons.
Must be the leptons because they don't feel the color. If you are here, you feel the color. You will get gluons to do this crazy thing to you. So you are a quark. So here in SU3, so this is a lepton. Very good. So which lepton? What is that? Tell me. It's very easy.
I mean, the electron and the
neutrino and electron. So look, if it is neutrino and electron and they are left-handed, remember in the weak interaction, this must be left-handed, you agree? All of them must be left-handed because you and I don't like to break Lorentz symmetry. I can't put a little bit left and a little bit right, because left is left, and it stays left under Lorentz symmetry. It can never become right. So everything is left. So who is here?
I mean, quarks of 3 different colors.
Yes. Which quark now? It must be one and the same quark because it's an SU2 singlet. So here is a quark, which I have to figure out which one. It's a left-handed quark. So it's really, is it a quark or? Left-handed quarks have weak interaction, but this guy doesn't have weak interaction. This is a singlet.
You should be right-handed.
Yeah, but he cannot be right-handed. He must be left-handed. So remember what I used to tell you. So here is the SU2. Why is this? I'm sorry, SU2 singlet. Look how, by playing a little bit, you can understand how we build the standard model. Look, when we have to do it. So look, this is an SU2 singlet. But remember when I told you, if you have a right-handed fermion, you don't have to work with a right-handed fermion. You can take a charge conjugate. Just a complex conjugate, multiply by some silly gamma 2 matrix. This changes chirality. Charge conjugation changes chirality. So the right-handed fermion is equivalent to the left-handed anti-fermion. Equivalent. So in other words, this is not a quark, this is an anti-quark. There, because it has to be left-handed because of Lorentz symmetries, but it must be right-handed because it doesn't want to interact with W. Well, it's a far star. That's left-handed, fortunately. But which one now? How do I decide?
Maybe of the first generation. Okay.
Yes. True.
But there is up quark and down quark.
Precisely. Which one? Here is here is the essence, one of the most beautiful physics that you can imagine. What I'm going to tell you.
Maybe down.
Down. Okay, we can make a poll. So this Q could be what you are saying, DCL. You are suggesting. Why did you say down? An interesting suggestion. Well, it's a 50%. You are saying how much can I go wrong, right? If I'm lucky, I'm right. So I leave a good impression. If I'm wrong, I can always say up. How to decide? Look what we said. When we started building the standard model, I have to, now let's go and step back. Step back. You see, we got to step back. This is what the fathers of the theory, they have to go back and say, let's try to see how it all started. By the way, the fathers of the theories are called Glashow and Georgi. And one of them is Glashow, okay, in 1974. He remembers how he wanted to build a standard model. Remember what Glashow tried to do? Glashow started with SU2L. This was Glashow's attempt. Well, his advisor told him, Schwinger. What is the charge in SU2L? In SU2? It's unique. It must belong to the gauge group, so it's T3. Did not work. Fails badly. These are not the charges in H. Okay, says Glashow. I'll take SU2 cross U1. So what is the charge now? Well, it must live inside of the gauge group. This is, he starts from 57 to 60. He's doing his PhD thesis on this, 1961. It's T3. A linear combination, because hypercharge is arbitrary, I can take like this. Now SU5. What is SU5? How many generators?
24.
24. Right, because U of SU5 is e to the I theta I Ti. These are 5 times 5. Ti's are Hermitian, but they are traceless. There are 25 Hermitian. There is one less. Traceless. By the way, what is the rank of SU5? What can tell me? The number of Cartan, those that commute with each other.
4.
4, because you can write only 4 traceless diagonal matrices, not 5. Okay, there are 24 generators, ranking 4, 24 generators. So that means that electromagnetic charge must be a linear combination of CI/Ti. That's what I mean by SU5. We can figure what it is, but I don't really care at this point. Why? Because they are traceless. I find that the trace of Q electromagnetic is 0. See, when I did SU2, I found out the charge is quantized. It cannot be arbitrary. The trace must be 0. Because of this tracelessness, the charge of different components is related to each other. There is actually a smallest charge in SU2, it's a half. It's a normalization that it's a half, but every other charge is an integer times a half. Charge is quantized. So it's here. The quark must be what it means, that the sum of the charges, if it is quantized, so I put it down here. I say some anti-quark, nu E. There are 3 of them, 3 colors. So what it means that 3 times charge of this anti-quark plus charge of the neutrino plus charge of the electron is 0. Q nu is 0, 3Q QC plus QE is 0. Charge is quantized. In the standard model, there is no correlation between quark and lepton charges. Completely arbitrary. Hypercharge is arbitrary, charge is arbitrary. So this means that Q is the down quark, as you said correctly. But charge is quantized. This is why so many of us got excited about grand unification. Because charge is quantized its nature, which is a miracle. Imagine that, imagine us, 10 of us, having our masses precisely integers times each other mass. That would be crazy. All the particles in nature satisfy this charge quantization. So obviously, the fact that the theory predicts charge quantization, and you have to build it, you have to put the other fermions. We are not going to do it today, obviously. This is not a course on grand unification, but I'm giving you a flavor that grand unification, this unification of the grand unification is deeply connected to the quantization of charge. And there may be those of you familiar, many, many years ago, Dirac said the following: I believe that there will exist magnetic monopoles. People said before him. Just like there is an electron, which is a pole of electric charge, I believe there will be a pole of magnetic charge. He managed to prove an extraordinary thing. Then he wrote the quantum mechanic theory of magnetic monopole, and he found something fantastic. That the product of the electric charge times the product of the magnetic charge is proportional to integer. An incredible thing emerged. If there is a magnetic monopole, even one is enough. Charge is quantized. Magnetic monopoles have been desperately looked for over the decades. The most fundamental prediction we can imagine. So Dirac says, if there is a magnetic monopole, in 1974, I don't remember the year precisely. Which year? I forget. I can see now why history may be relevant to you guys. I remember very well the years when they were part of my life, but before that it wasn't. Well, some I do. Anyway, in the 30s, I think. In 1974, at Khoft and Polyakov show a very interesting thing. So Dirac says, if there is a monopole, charge is quantized. They are showing if charge is quantized, there must be a magnetic monopole. So the people got even more excited. Since so many of us fell in love with grand unification, and the theory predicts that there must be magnetic monopoles, you can imagine how exciting it is. That's unfortunately has never been seen. I have been thinking about monopoles all my life. I have written a few papers, not that many. I've written many because it's not easy to come up with meaningful work on magnetic monopoles, but they are obviously an extraordinary fascinating. This is really a research. Imagine if you're working on magnetic monopoles, that you can tell any cashier, anybody in the street, every child has tried to. This is great physics, okay, working on magnetic monopoles. And it's a part of particle physics. Anyway, not yet seen. There was a dedicated experiment called macro, magnetic something, at the Gran Sasso laboratory. In the Italian Apennini, Gran Sasso laboratory, not so far from Rome, about an hour and a half drive. Macro experiment put the limit that the flux of magnetic monopoles is less than about 10 to the minus 16 per centimeter square per second. That's how many you get, whatever that means. I mean, who won't mean very much this number to you, just mentioning it. So this was first and fundamental prediction of grand unification. Actually came second. The first that was noticed is also fundamental. What happens if I put quarks and leptons together? So grand unification is this, quark becoming a lepton. What do you think will happen? I will violate a baryon number, a lepton number. In a grand unified theory, obviously, delta B will not be 0. Just like in the standard model, you violate a neutrino number. In the standard model, neutrino becomes an electron. That's what the W does. Really what you are saying is, look what you are saying. When I wrote this 5-dimensional thing, nu E, we are saying that there is a W changing. And then there was DC of different colors. Why don't I do it for once nicely? Maybe I'm changing the orders, forgive me. So what is happening here, I can go here from one to another. These are doing from the gluons. But it means that there are new gauge bosons that can go, that's what the gauge theory means. You can go anywhere inside the group, you can move. We call them X, new X gauge bosons. So what does W do? Makes down quark become up quark, and then can give me. What will X boson do? Can violate the baryon number. So proton could decay into what? Give me an example of just what you think. Let's try to write something that can violate a baryon number. When the baryon becomes a lepton, this is what's going to happen because a quark is becoming a lepton. So what can I have? Proton can become?
Positron.
Positron. Okay, well, someone said positron, so let's make it positron plus, and then something neutral. Could be a photon, could be a pi 0, maybe. I don't know. Whatever. Something which is carrying no fermion numbers because we are not changing a fermion number. Quark is going to a lepton, that's a fermion becoming a fermion. There is no supersymmetry here. I'm not doing anything sort of dramatic. Well, this is quite dramatic. Or someone wanted to go into neutrino, right? But then I should put what? Well, pi plus, for example. Something to, gives me conservation of charge. I'm not violating charge, and so on. When this was predicted, you can imagine that people went crazy about it. Literally. And never found a proton decay. Do you know what the limit is? Comes from SK, which is super Kamiokande experiment in a mine in Japan. You go deeply. You know why? You know how you do this experiment. You take a swimming pool full of water, sit down by the pool and wait to see. You need a lot of protons because the probability is small. You just wait. The problem is that you get cosmic rays, so you cannot do in the swimming pool. That would be beautiful, imagine having a nice open air swimming pool somewhere in California, I don't know, Florida. You can't do that because cosmic rays come. So you gotta go and shield these guys. So it's not so nice. You go deep down in a mine. A lot of engineering. So what's the limit on proton lifetime?
Ten to the 34 or something.
Yeah, very good. Bravo. It's surely 10 to the 34. It's getting even better in some channels, but we can conservatively say, you see how amazingly long that is? To remind ourselves, what is a muon lifetime? mu decays into an electron? You know, roughly?
Ten to the minus 3 or 4 seconds.
Yeah, well, it's a little smaller, 10 to the minus 6, I think, roughly there. We could even write 10 to 3, 4. You know, look at the difference. This is a natural lifetime. And this goes through the W decay, right? Through the W exchange. Agree. By the way, what about neutron decay? Why did I ask you about muon decay? Neutron decays into a proton plus electron plus nu bar. So this lifetime term mu is 10 to the minus 6 seconds. What about tau neutron? It should be faster, right? At first glance, because neutron is heavier than the muon. But it's not. If someone remembers? It's about 10 to the 3 seconds. It's much longer. Why is it longer? It's again going through W. Why is tau neutron much bigger than tau muon?
Because muon is a fundamental particle.
No. Who cares? I mean, here, down quark is decaying into an up quark. No. If you let a down quark decay into an up quark, neutron will decay. Well, in order to decay, there must be a big mass difference. Muon is much heavier than the electron, but neutron has the same mass as proton. It barely decays. See, 10 to the 3 is an enormously big number. It's 9 orders of magnitude, billion times slower. Why? Because mass of the proton is so big that there is no phase space, basically. Please remember that m proton minus m neutron over m proton plus m neutron is like 1 in 1,000. It's really small. This is why this is a natural lifetime. So see, the natural lifetime is this. 10 to the minus 6 seconds. But remember the decay rate. So how will the muon decay? Well, muon will decay. Muon decaying into an electron plus etc. is the exchange of W. And proton decay into will be exchange of the X bosons. There'll be some quarks, right? We have to let the quarks decay, and there'll be quark, 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 and lepton. I need 3 quarks. We can draw this very carefully, but I just want to now do a lazy person's approach. Lazy person's approach, which, by the way, works beautifully. Sometimes being lazy is great. So this amplitude is proportional to 1 over mw squared, remember? And this is proportional to 1 over mx squared, mgat squared, the new gauge boson mass. So in other words, gamma mu decay is proportional to 1 over mw to the 4th times m muon. On dimensional grounds, what will it be? It will be the mass on the muon to watch power?
5.
5. I need to get a dimensional mass. And the gamma proton decaying into whatever we said, say positron plus pi 0. You know why you like the positron better than neutrino? It's just easier to see it. So people looked more. This is the main channel. People look to like that. This will be proportional to m proton to the fifth power. That's the heavy particle divided by mx to the fourth. So we can put the numbers. We can think a little bit about let's take a little break. I know today is a sort of light lecture. It's not, I'm not giving you, by the way, please pay attention. I'm not giving you any rigorous analysis of anything. I'm giving you a flavor of what emerges from this new physics of grand unification and why this is so interesting. But I suggest we take the break and come back to the numbers. We should find out mx. If you do it, I will really appreciate. I know that tau p is bigger than 10 to the 34 years. Tau muon is 10 to the minus 6 seconds. From here, I should find out that mx is bigger than what? If you were to do it during the break, I will pay you a coffee. If you were at the ICTP, I would take you for coffee or something. So we are not gonna meet, it seems, in any, I want to be vaccinated before I move. Look, let's meet at 12:10. Let's just take a 5-6 minute break. Try to guess if you're lazy, but you can put the numbers very quickly. I'm a few minutes late, so I'm sorry. My coffee maker is slow. Anybody put a number? Anybody wants to help me? No. I have to do it on my own.
I got around 10 to the 15 GeV.
10 to the 15 GeV, yeah. It's not surprising. Very good. Thank you. Because why? Tau proton is mx over mw to the fourth. It goes, tau is, after all, tau is 1 over gamma. And then that means mu1 over m proton to the 5th power. So we know everything. Times tau mu1. Here it is. This we know. This we know, 100 MeV. This we know. This we know. So from tau p bigger than 10 to the 34 years. Thank you, you got it. You put it in second. You found out that mx must be bigger than 10 to the 15 GeV. So you see what is very interesting, however. Now you can appreciate the little miracle. Now you go back in the picture. Let's go back. Because it seemed that something non-trivial happened. No, here. Look, the scale is 10 to the 16 GeV. But this has to be bigger or equal to mmx. Unification cannot occur before we hit the scale of new particle. What is the unification? That's where the new particles are residing. Electroweak unification takes at the scale, which is around the masses of the W and Z. So what we are saying, look, it's true that two couplings will unify. We are saying that m got must be bigger than 10 to the 15 GeV. But also, if to make any sense, it must be much smaller than m Planck, which is 10 to the 19 GeV. If it is close to 10 to the 19 GeV, I cannot compute anything. I don't know how to compute when gravity gets strong. At that scale, you better work on quantum gravity. Of course, some of you want to work on quantum gravity today. I've always struggled understanding that, because that's to me like working on the probability that my cup is not falling down. Actually, there is a bigger probability that my cup is not falling down than the fact that quantum gravity has impact today, but okay. We don't discuss tastes. I appreciate. I have a close collaborator friend, Guy Advali at LMU, in Munich, who works a lot on these issues, but in a sense of understanding the theoretical aspects, I can't quarrel to that on the physics of black holes. So now we have a little miracle, and the unification takes place precisely where it should. Then you get excited. This is the work of George E. Queen and Weinberg. George E. Queen and Weinberg. The same Weinberg. The same George I did. And Helen Quinn, I should emphasize, one of the rare women at that time, maybe around 75. They looked at all the three couplings and they got the following picture. Alpha, energy, this is in the standard model. SU5, I mean the standard model particle, the theory would be SU5, you run the standard model particle. So you got SU3 and SU2 meeting, 3, 2, and then they put U1, and lo and behold, what happened? They got them to meet. The world went crazy. As Maurice Goldhaber, my ex-colleague, Maurice Goldhaber, a great experimental physicist who measured the helicity of neutrino, said, everybody rushed underground. The whole world, everybody went underground. the whole world started to do this experiment. From Europe to India to what you name it, to Japan, to so on, looking for the proton decay at the scale of 10 to the 16 GeV. That was very exciting. Very, very, very exciting. The reason, the way do you run, the thing to run in SU2, you see the meeting of couplings depends. You see, you have to know, in order to follow the couplings, you have to know G prime, G2, as we call it, which I call G often. G2, the SU2 coupling, right? I call it G. And you need to know G3, which I call G strong. And this is the U1 coupling. But in order to know G prime, remember tangent theta W is G prime over G. And in the 70s, sine theta W was cited as 0.20 experiment. It was wrong. This is before lab. Unfortunately, it was wrong. This is wrong. But this is what they used here. So the picture was wrong. The way it looks, unfortunately, we got excited for wrong reasons. Well, even SU2 and SU3 meeting is very exciting because we are meeting at the energy scale. It's a little miracle. You could meet anywhere above MW and you are meeting below M Planck and above 10 to the 15 GeV. So the picture that is right, it looks like this. This is the standard model picture. SU3, SU2, and U1 goes here. There is no unification. Or the SU5, if you wish. No unification. Why? This is a true picture. Because today, sine squared theta W, it was measured in the 90s, is 0.23. So you get this picture. In 1981, people were everybody was excited about supersymmetry. So some of us, there was the original paper was, who was that? Dimopoulos, Raby, Wilczek in 81. And then a more detailed analysis was done by Marciano, my colleague. We were at Brookhaven. I was working at Brookhaven in the fall of 1981. We decided to look, what about Susie grand unified theory? How would you do Susie without studying Susie? Remember what I told you, 1 over alpha at E2 is 1 over alpha at E1 plus B over 2 pi logarithm E2 over E1. B is 11/3 TGB minus 2/3 T fermion minus 1/3 T scalar. What will happen when so this is B normal. What happens when I look at the supersymmetric theory? What would be B supersymmetric? I need your help. Remember, the gauge bosons will have a partner. The gauge bosons have a partner which are gauginos, which are fermion. So it's 11/3 in an ordinary theory. What about symmetric, supersymmetric theory? What should the coefficient be? Let's do this and we can split for the day, for the week, for the year.
Is
What
it 11/3 minus 2/3 there?
Precise. Because fermions contribute 2/3. And they have exactly the same quantum number in the gauge bosons. They are partners of the gauge boson. So you put 2/3 here. Very good. I need more space. So let me do like this. I'm showing you that you can do supersymmetry, a lot of it, without knowing nitty-gritty. There is a lot of information you can extract. Minus 2/3. Now T fermion. How will the T fermion look like? They have partners. Fermions has a partner, which is a fermion, which is a scalar.
So plus 1/3.
Plus 1/3. That's for the scalar contribute. Even the name fermion is not such a good name, but you know, by fermions, we mean quarks and leptons. In supersymmetry, there are no fermions or bosons. There are only superfields. But we reserve the name. We speak of gauge bosons because they are gauge bosons or they are messengers of interactions, and then we call gauginos. So scalar fermion, it's a bad name. So T fermion minus, and I have to put the plus sign because fermions and scalar enter with the same sign. 1/3 for the scalar. Of course, I should add the fermions. Why? Because the scalar is like the Higgs, has a partner which is a fermion, Higgsino. Yeah, is a fermion. And this is my Higgs. By fermions, I mean quarks and leptons. And by gauge bosons, that's obvious. So it's 2/3. So notice that I will get the same coefficient. Sorry, T scalar. Because of course, scalars are equivalent to fermions. Scalar have partners which are fermions. And so the quantum numbers may differ. So it's not 11/3, it's 3 TGB. It's just a different coefficient. Minus TF, minus TS. And I want to tell you something interesting. In 1981, when we did this serious analysis with my colleague Bill Marciano, we predicted we could get unification in 1981, but sine squared theta W had to be 0.23. But remember, the sine squared theta W at that time experiment was 0.20. So if you're very interested, if you want to read our paper, Marciano is the only one paper. Actually, I'm very proud of that. On page 4, we said that we believe that supersymmetry is good. And we believe that sine squared W should be 0.23, that the experiment is probably wrong. And the reason is, people used to quote it. This is what they should have written, the experimental people. It was 0.20 plus with some coefficient rho minus 1. This is really what they should have written. Remember what rho is, or maybe I never defined it. Rho is called mz cosine square theta W over mW square. This is a famous rho parameter of the standard model. Can you tell me what is this at the tree level? What is it? It's 1. This is the main prediction of the standard model. This is Weinberg's paper. Remember, this is how you predict MZ from MW. This is at the tree level, but you have to include the loops like this. For example, Z boson and the top quark. Top quark is very important. Today we know, but at that time, let me just tell you, you get a contribution which is alpha over pi, m top square, minus m bottom square, which is small, mw square. So what we said that we believe that m top is 200 GeV, roughly, in 1981. Let me just tell you. And everybody told us we were crazy. There were a few things in my life. This is a message to you young people, you know, don't pay attention what people tell you. When I was working on a neutrino mass in the 70s, everybody told me I was crazy. Well, not everybody. Salam didn't. It turned out neutrino is massive. People knew. This is very interesting. They say, how can top quark be so heavy? This is not natural. You will go to seminars and people will tell you that what they know should be natural numbers for something called cosmological constant, for the Higgs mass. They will invent some reasons or other to tell you what the parameters should be. So in 1981, everybody was sure. You see, if top quark is very heavy, then rho is bigger 1, then you can get 0.23. So in some sense, you see, people got in 1991, LEP measure sine squared theta W. This is a true number of the experiment. It's 0.23. This is in 1991. And then Tevatron found the top quark with a mass of 175 GeV in 1996. It took 15 years. It turned out to be true. So in other words, Susie unification works and was predicted. And it was tied with a top quark mass of being very heavy, completely different of the other models. So one of the reasons that the supersymmetric guts became very popular over the years, people are still working on them. Supersymmetry was desperately searched for. Unfortunately, I have to finish my course. I wanted to hoping to give you some door to new physics, the beautiful physics of monopoles and proton decay and maybe supersymmetry. Unfortunately, not a shred of evidence, neither for supersymmetry, nor for proton decay. And monopoles, what is very interesting, by the way, this made grand unification die. About 10, 15 years ago, I decided I don't want to work on the theory in which there is no experiment. People stopped doing super Kamiokande, stopped. But now they are getting new funding, both they and the Dune experiment in the States. And we are seeing revival of grand unification. I just want to let you know, those of you that want to work on beyond the standard model, there is a beautiful physics which is very much under control, not so speculative, but under control, in which the experiment will come back. And it's good to be, you know, for you young people, you want to work on things that the experiment can probe. I left grand unification. I'm thinking of coming back. I've actually even studied to do some work because I like to work on things that can be measured. So I was doing a lot of physics that was related to LHC. As I try to argue, neutrino mass could be probed by the LHC, the origin. These are kind of the main phenomenological roads that have dominated our field. The theory of neutrino mass, the possibility of supersymmetry and the grand unification with its exciting predictions. Notice that this thing about grand unification I'm telling you about grew out of, it's beautiful, grew out of, not outgrew, grew out of QCD theory of strong interactions with an extraordinary speed. Asymptotic freedom in 1973, only a few years later, it was all understood how the growth of couplings or the falling down related to new fundamental physics. Oh, you lost me?
Yeah, I think he changed the screen.
I have a problem. Well, I don't know, maybe we'll write nothing else. I probably have to stop sharing and restart it if there are more questions. Tell me, anything you guys want to chat about? Today was obviously a very relaxed. You see what I try to give, just to give you a sort of a picture a little bit.
One question, I mean, not a technical question, just
Just write anything. Let's chat a little bit, guys. I won't see you again until exam.
yeah, I mean, I was just asking, what's your feeling about the new physics coming in the next few decades? I mean, which direction it might go?
I wish I knew.
No, I mean,
You should ask me the following. Let me tell you how you could ask me. What are you betting on? Look, we physicists like to bet a lot. I'm a compulsive bettor in physics. I don't bet on anything else but I bet in physics. You know, it's sort of, it's like when you're asking what I believe in, it's very easy to tell you. I remember Weinberg was giving us a colloquium last year. When was it? And he said, oh, I think you guys should be working on this. Then he admitted, but that's not what I'm working on. It's easy to tell you what you should be working on, you know. So even what I'm working on, you may ask me, do you believe in what you're working on? And I tell you, of course, I'm writing papers, I believe. That's, you know, if you write papers, you can get a good salary, you know, and have a good position. So I'm betting on, and I'm bound to lose money, that the two things will happen, that neutrinoless double beta decay will be observed. That will imply new physics related to this extraordinary thing. I have been fascinated from the first day when I became aware of that. And I became aware of that by accident, sort of. I have been working in neutrino mass from the beginning of my PhD because I fell in love with this idea of left-right symmetry, and neutrino was massive and it was very messy. The mass of neutrino was messy. How in the world could neutrino be lighter? And then I came across, someone mentioned it. And actually it was very interesting. I was a postdoc in Maryland, young postdoc, and we had a visit by a guy, a young postdoc at that time in Princeton or Harvard. No, he was in Harvard. You have heard his name, the guy called Witten. And it was very interesting. He was younger than me, and we were It was something mind-boggling about this guy. He was working on 10 different things. And I said, I'm interested in neutrino mass. He says, maybe you should think it's Majorana. And I wanted to kiss him. I said, look, wait, they don't see anything else. He said that. I went home. It was very easy. I was working on that. And with my friend Mohapatra, we could come up with a seesaw mechanism because of this extraordinary work with Majorana, that a particle can be antiparticle. So I'm betting the neutrino double beta decay will be observed, and then that LHC will find the traces of left-right symmetry. I'm betting to the following degree. Was before the COVID, I've in the last couple of years, 2 years ago, I had a very heated, very feisty, very, very strong fight with Weinberg he was giving a summary talk in the 50 years of Standard Model. He is a father of this great Higgs thing. And he was saying he shouldn't work on neutrino mass because that's hopeless. And I got very angry and there was an exchange and so on. I got invited by Weinberg to Austin. So about 2 years ago now, a little less, I went to Austin and at least in public there, I managed to convince him. And then I've just finished some work that shows that this is a self-contained theory. I'm answering you along, you will forgive me. And so after being for 5 years, I was in a self-imposed isolation for 5 years. I didn't go for meetings. I wanted to finish this work with my collaborator, Teo, our ex-diploma student, who did very important work in this. So I was giving colloquia all over the world, literally. I was on a world tour. I'm very proud, without drugs. The rock stars do that, okay? But they take drugs, okay? I don't take any drugs. Okay, convincing the world. And in one of these places, okay, people tell me, but you really believe in this, okay? I said, yeah, sure. Would you bet on this? Yeah, sure. So I ended up betting my monthly salary. That's a lot of money. I have a good salary. I have a lot of other bets, okay, that 10 years or so from now. This is a very serious bet. If I die, my daughter has to take over my bet and so on. So this is what I'm betting on. This is one thing. I would also be willing, I don't know why I do that. I have a hunch that the next generation of proton decay will see it. You see, the question is what the experiment will do. The theory may move in any direction. When there is no experiment, then the situation is very dangerous. You see, then it depends on who has power. We have lived in that era. That's not good for physicists. The way I like to put it, I like democracy. For example, I prefer to live in a democracy than in a system without it. I've lived without democracy. Democracy is better for me. Now, democracy in physics means experiment. So maybe the way you would ask me, what do you think experiment would discover? I could bet on proton decay. The next generation. There is something beautiful about this natural scale of grand unification, just right. Just there. I used to bet on supersymmetry. I don't do that anymore. I don't know why I lost my faith. I can't. Yeah, I think what bugs me is that I can't make predictions. I don't know how you guys feel, and obviously to some of this will fall on deaf ears. I cannot appreciate the beauty in physics if there is no predictivity. An example, when I thought the Standard Model, I was your age. To me, it was terribly ugly because I was sure that the world should be symmetric, left and right. But I was fascinated by the beauty of the theory making these crystal clear predictions. So I knew I should work on that. And maybe on something that breaks down to the Standard Model. Okay, so predictivity. So in summary, I don't have hope. Unfortunately, magnetic monopoles, people are not looking. They're looking at them, but not with the same dedication. I wish they would do more. I think maybe that's what you're asking me. What could be the fundamental experimental discoveries? You know, you've heard these days that maybe G-2 experiment, the Monopole, is revealing some new physics. That, of course, they are selling it in newspapers. That's okay, but there may be some new scalar. It may not be some fundamental new physics, really. You know, the standard model could have an extra scalar particle added to it. It's, of course, it's great, but I also hope, as you guys do, that there will be some surprise. Not just for my sake, for you guys, for your guys' sake. You know, your generation needs some luck now too. I was lucky when I started out. I hate to see you guys go just to formalism. I've tried. My duty is, you know, I have a mission when I teach at ICTP. This year it was very hard for me to teach here. I had to teach every day, which was hard on you guys. I'm really sorry because the schedule, it starts late and I had to finish by now because I have another commitment. But I have a mission, not just to teach you the standard model, to show you the beauty of making predictions with quantum field theory, which is our best tool. Anything else? We could have questions like this if you wish. So you know what I'm betting on. You can offer me, you can write to me and offer the bets, and I will give you good odds because your salary is smaller. So by the way, I just wanted to know we will give you still a couple of more tutorials as I finish the course. I'd like to have a few more homeworks. Remember, please, homeworks are indispensable. They make all the difference. You boost your grade tremendously with the homework. Do them. At least 2 more. And what I understood now, I think this is the final decision. We'll have an exam after GR, which is in May. By the way, what else do you have? Me and GR? Is there anything else, or it's all QFT? What's the story with QFT?
We already took that.
It was already?
Yeah.
When?
Before JAR and standard. So we are taking them like two courses. Once like standard module and JAR, and then
Right. There was a shift in the dates, right? I should have, you know, I'm as you know, I'm an emeritus, like my colleagues may know. I've become a faculty in Munich at LMU University. Is there any of you, I've asked you, but it seems not interesting in neutrino physics? I thought there was.
Yes.
Yes, you are.
Yes.
Logan. Because I told you if you're interested, I'm giving a course, a whole semester course on the issue of neutrino mass, the physics of neutrinos. You could be included if you wanted.
When does the course start?
I just started today, but he was chatting today. I was sort of reminding them of some of the things about the standard model. Not really. The course is kind of complementary to the standard model. It's the things that you don't have to touch. I have a colleague, Dwali, who teaches the standard model, and I make my course complementary. I go a little bit above, beyond the standard model, a little bit behind, a little bit below. Sort of, you know, neutrino was the main protagonist. As you could see in my course, I couldn't speak about strong interaction. That's a subject in itself. So I just decided to give you a little flavor of that. And concentrated on the electroweak part. And neutrino was the main protagonist in the past. It all started with neutrino, and now, of course, neutrino mass it's our best bet. I mean, on this, when you ask me, okay, that's got to be a motivation for new physics. That's the only incompleteness of the standard model. There should be no other thinking. There is all the things that people tell me as secondary things. I don't understand that. You should attack the theory where it sort of failed, where it was incomplete. So if you find out that the measurements of mercury perihelion don't agree with the Newton theory, you should work on that. Well, Einstein worked before, actually. He managed to build a theory at the time when the data were coming out. It's interesting, more or less at the same time. Maybe even the mercury perihelion came out before even. I'm not sure, around that time. Anyway, if those of you, they decide to listen to it, you know, just send me a message and you could be included. And then, you know, the advantage of Zoom is that you don't have to listen to anything. You can. So how is it going? I can ask you guys. How is it going with this Zoom thing? Are you happy with that? Is that, or you prefer in class?
I personally do prefer in class.
You prefer in class? My God, I prefer so much Zoom as a student. I'm very happy with their conferences now on Zoom and so on, because I can decide how seriously I want to listen to you. Say you're speaking, I can. Yeah, in class, what if I'm boring you in class, what do? You have to sort of pretend that you're listening, right? And maybe you're sleepy, but still you prefer it. That's interesting. Other people?
Same in class.
Same in class. It's interesting. Is sort of to be the part is the social thing, or of course socially I can understand that. No, this isolation is not fun. No, that I have no doubt. But I mean, as far as the following the course.
Yeah, I mean, that's what I meant.
Even the fact that you can get the lecture notes in real time, whereas the Blackboard gets erased and then you have to listen to the recording again, which is sort of boring.
There are some advantages like that, but I don't know. I think having in class or lectures in class, it's I don't know, better for me too.
Well, I like personally, I like the stage. I like to be on the stage to some degree. I'm a frustrated actor, I guess. There is a part of me that, you know, there's being on stage. It's another thing, you know, I'm kidding, is that when I'm teaching in class, I can talk to you guys. Some of the art of transmitting your passion and authority, you know, I like to talk about the things that I really think I care about. And that, of course, seeing your audience helps you a lot. But this is fantastic. So we are talking with a lot of friends. We are deciding when we start in class to do a hybrid teaching, that you do the mixture of, you can sit at your desk, write on your iPad certain things, write on the Blackboard essential. So you never have to erase anything. The essential forces stay on the Blackboard, and then some formula, and so that you can send your notes immediately. This is becoming, you know, we are debating a lot how to, once this is over, how to proceed. Okay. Guys, contact me, write to me if you have, oh, by the way, do you want to meet? Do you have questions? I could schedule another meeting that I called office hours. I haven't done that, not knowing. Is there any of you that want to meet with me and discuss some of the things I've said recently? You look, sleep on it and write to me. When you write, please do always reply all so that we all receive it. It's good that everybody sees what is involved. We will easily organize it now. There is time. One of these afternoons. Okay. Wish you best of luck.
Thank you very much.
Thank you. It was a pleasure. I wish I could get to know you, but
Are you going to come to Trieste at some point?
I'm in Trieste because I got stuck with Germany is closed completely. Munich is, I decided I've been stuck for a year. I am actually in Trieste. I'm not going to my office. I want to be vaccinated before. And apparently my age is coming, my age group is coming. Well, I have to, okay, today I was busy teaching, tomorrow, I know it's still on time. It's when you call, of course, it's very busy. So then I'll come a little later, but I've decided not to go to Munich because everything is closed. So you don't want to go to a new place. I've studied this position about a year ago. By the way, those of you that like to do, it's not an easy place to get into, but it's a very, very good place. Those of you that want to be interested in gravity, there is my colleague Vali, who is doing beautiful work on black hole. They really, I think the only serious work that matters to me, which is not semantics, he's trying to understand black holes. Just the way you and I should think about black hole as the conglomerate of tightly packed gravitons and quantum mechanical system reproducing, the first thing he did, reproducing this sort of mysterious formulas of entropy and area and so on that somehow are mind-boggling, okay, just through the language of particle physics. And the next step, of course, in the black hole physics would be to, I don't know if any of you are aware of this, please feel free to leave. I just wanted to tell you there is the celebrated work of Hawking that made some people even think of changing quantum mechanics. He himself was advocating that, which was crazy. When Hawking derives his temperature, you see the black hole have these characteristics of a perfect black body temperature. So you say, oh, but then what happens if I throw a book to the black hole, into the black hole? If I throw it in the sun, I can reconstruct the book. It's not easy, but from the ashes, in principle, it's not an easy thing. Whereas if the black hole has only temperature and nothing else, then of course all the information is lost, which is kind of very strange. Now this is derived, and it's amazing that most people don't even know it. There are people that work on they want to work on that. In the limit of infinitely massive black hole and infinitely weak gravity, you let G Newton going to zero. So if you think of a black hole full of gravitons, it's like having infinitely many gravitons. Think of n gravitons, n going to infinity. You keep the radius fixed. You know the radius of the black holes, all of you, right? It's G Newton times mass. So you keep R fixed, G Newton to zero. That, of course, is infinitely large n. Now you should compute the corrections 1 over n. And it turns out that the temperature varies, okay? He has been arguing, among other things, that there is nothing mysterious about black holes, that there is nothing that you have to change about quantum mechanics. This is a very interesting thing. Another interesting thing for those of you that like to think about gravity, that this was the original idea is due to at Hooft. You see, everybody has been telling us since we were born that gravity is not good when you go to small distances. True. So they tell you it's not good when you go to high energies because high energy is a small distance. This is uncertainty, right? So if I cannot do it at high energies, how can I have a field theory describing gravity? But what the Hooft said, and Wally has been pursuing more seriously and his collaborators, when you go to very, very high energies above the Planck scale, what's going to happen? Imagine the scattering, a two-body scattering, when you actually manage to scatter them with enormous energy bigger than Planck mass. Well, according to Einstein theory, you should produce a black hole. And the radius of the black hole should be energy times G Newton. Remember, in Einstein theory, mass gets traded for energy. The R over black hole is not 1 over energy. It's energy times G Newton. So in other words, the Einstein theory could be actually good. All this claim that you have to modify Einstein theory, and some people had a scalar, they're called Bragg-Decay, some people had 2 scalars, some people had 5 particles. In the string pictures, you had infinitely many particles, which you can nicely describe by a vibrating string. This may be wrong. By the way, none of the theories improved Einstein gravity. None of them are renormalizable. String theory failed in this sense. But there is a very beautiful possibility that Einstein theory actually saves itself. It's called classicalization, that you never go to the small distance. So I just want to tell you, those of you that like that kind of physics, I would suggest that one of the places to apply to would be LMU in Germany, which has an excellent PhD program, also a master's program. If you think that you need more courses and so on, they have a very, very good master's, but PhD is more logical. Okay. And the reason I'm saying, you know, I can be of help in getting you there, depending, of course, the grades should be good and so on. You can try. Since I'm kind of live between the two places, my heart is still at ICTP. I don't know if you guys know, I've been involved with the, you cannot believe what diploma meant. I think I had more than, I must have had at least 70. I have supervised an incredible amount of summer thesis. It's one of the great things. One of the reasons that I stayed at ICTP was a diploma program. I used to lecture. I used to come in the 80s. I used to work in the Brookhaven National Lab in the States. And then Salam would invite me in the summer. I fell in love with the, you know, how can you not find the love? You know, we are all there from the whole world, right? There is something special about us being there. And I fell in love with Italy. And so I've actually come to ICTP to build a phenomenology group. Salam had given up. Unfortunately, there was a tragedy. Salam got, just when I joined, he got Parkinson, and Salam would die a few years later. But Salam has given up on phenomenology and worked on strings and Kaluza-Klein, and then he regretted it deeply. He actually told me once with tears in his eyes. So I came to ICTP to build a phenomenology group. And actually, we managed to build a good group. I got Smirnov, and we had Wally for a while, and so on. But my main attachment, honestly, was the diploma program. So for me, it's really a joy to teach you guys. If you enjoyed half of what I do, you know, you're having a good time. You could see that I like to transmit what I care. On this note, unless you write to me, I won't see you until the exam. So best of luck.
Yeah, thank you very much.
Yeah.
Take care.
Thank
Bye
you.
now.
Bye.
Thank you.
Bye.
Bye-bye.